Hello! In this video, we are going to prove the following theorem. Suppose a and b are real numbers where b is non-zero. Then the negative of a over b is equal to negative a over b, which is equal to a over negative b. Now in this series, we are using a list of 10 axioms for the real number system, and I'll leave that list of axioms in the description below. Now, axiom 7 tells us the following. We have, for all non-zero real numbers x, there exists a real number which we call the reciprocal of x, that has the property that x times the reciprocal of x is equal to 1. Now, using axiom 7, we define the operation of division as follows. Suppose a and b are real numbers where b is non-zero. We define a over b to be a times the reciprocal of b. And now, here are some results that we have proven. Given any two real numbers a and b, we have negative a times b is equal to a times the negative of b, which is equal to the negative of ab. Also, negative a times negative b is equal to a times b. So in particular, in L2, if we take a and b to be 1, well then we have negative 1 times negative 1 is equal to 1 times 1. And axiom 6 is the axiom which discusses the existence of this real number 1. It tells us that 1 is not equal to 0, and we have 1 times x is equal to x for all real numbers x. So in particular, 1 times 1 is equal to 1, and 1 is not equal to 0. Well, the claim is, not only is 1 not equal to 0, but negative 1 is not equal to 0. And to see why, assume for a contradiction, we instead have negative 1 is equal to 0. Well, then we have negative 1 times negative 1 is equal to negative 1 times 0. And we have proven in our real number system that for all real numbers x, x times 0 is equal to 0. So we see from this, negative 1 times 0 is equal to 0. But we just showed that negative 1 times negative 1 is not equal to 0, so this is a contradiction. Our assumption that negative 1 is equal to 0 led us to a contradiction, so we must instead have negative 1 is not equal to 0. Because negative 1 is not equal to 0, well then, by axiom 7, negative 1 has a reciprocal, and it has the property that negative 1 times the reciprocal of negative 1 is equal to 1. But we've just shown that 1 is equal to negative 1 times negative 1. So then, if we divide negative 1 on both sides, or in other words, we're applying the cancellation law multiplication, this implies the reciprocal of negative 1 is equal to negative 1. And so we're going to be using this fact to prove this theorem. We're not going to need this result, so I'm going to replace this result with this result. And another result that we're going to be using, which involves the reciprocal of non-zero real numbers, is the following. Suppose a and b are non-zero real numbers, then the reciprocal of ab is equal to the reciprocal of a times the reciprocal of b. Now remember, we have proven that the product of two non-zero real numbers is a non-zero real number. So ab is a non-zero real number, so according to axiom 7, we can make sense out of the reciprocal of ab. And finally, the other preliminary result that we're going to be using is as follows. We have, for all real numbers x, negative 1 times x is equal to the negative of x. Okay, so now we're going to get into proving this theorem. But before we prove it, let's first make sure that this statement makes sense. Now, since a and b are real numbers such that b is non-zero, certainly, by definition of division, we can make sense out of a over b. And certainly, negative a and b are real numbers where b is non-zero, so this fraction makes sense. But what about this fraction? Certainly, a and negative b are real numbers, but how do we know that negative b is non-zero? Well, we know that negative b is equal to negative 1 times b, according to L4. And we've just shown that negative 1 is non-zero. B is non-zero as well. And as we mentioned before, product of two non-zero real numbers is a non-zero real number. So this is non-zero, and therefore negative b is non-zero, and that's why we're able to make sense out of this last fraction. So now let's get into proving this theorem. And to prove all three of these are equal, we're going to establish chains of equalities. Let's first show that these two guys are equal. To do that, well, notice, by definition of division, a over b is equal to a times the reciprocal of b. So we have this. But then, according to L1, we can rewrite this as negative a times the reciprocal of b. And then applying the definition of division again, this is just negative a over b. And so what we've shown here is that these two guys are equal. Now we're going to show that these two guys are equal. So again, by definition of division, we can rewrite this as negative of a times the reciprocal of b. And then applying L1 again, we can move the negative sign to the reciprocal of b. So this is just a times the negative of the reciprocal of b. Now actually, maybe we should put parentheses around this, because what we're going to end up showing here is that this guy is equal to this guy. So we don't want to get these two confused. That's why I put parentheses around it. But the claim is that these two guys are equal. And to see how that happens, well, first, by L4, the negative of the reciprocal of b is equal to negative 1 times the reciprocal of b. But then, by L2, negative 1 is equal to the reciprocal of itself. So we can rewrite this as a times the reciprocal of negative 1 times the reciprocal of b. And then, by L3, we can combine these guys together. This is just the reciprocal of negative 1 times b, just like that. But then by L4 again, negative 1 times b is equal to the negative of b. So this is just this. And that's exactly what we wanted to arrive at. So then by definition of division, this is just a over negative b. So through this chain of equalities, we have shown that these two guys are equal. So because we've shown these two guys are equal and these two guys are equal, that tells us that all three of them are equal. And so this completes the proof. And so yeah, that's pretty much it for this video.